This is chapter 10 from Stu Short. It says Master Math Mentor AP Calculus AB exam. He's given me permission to post these videos. Chapter 10, we talk about derivatives of trig functions. If we look at this definition, trying to find the derivative of sine, there's not really a whole lot we can do with this with what we know so far. If we were to let the limit as h go to 0, we would plug in 0 for h. And when we plug in 0 for h, we get sine x minus x in the numerator. We get sine x minus sine x in the numerator, which is 0. And we get 0 in the denominator. So 0 over 0, we can't really simplify that at all. So let's take a different approach. Let's look at the graph of y equals sine x, and let's see if we can estimate the slope of the tangent lines at certain points. So if we look here, tangent line would look something like that, pi over 4. Be not quite as steep as 0. Pi over 2 would be a horizontal tangent. 3 pi over 4 looks like it would be the same as pi over 4, just negative. Pi, a little bit steeper, looks like it would be like 0, just a little bit in the negative direction instead of positive direction. Pi over 4 would be not quite as steep. 3 pi over 2, 7 pi over 4, if we just were to sketch these tangent lines. So it looks like a lot of these numbers are similar. They are just positive or negative. So if we look at 0, slope of that tangent line is 0, looks like it's approximately 1. At pi over 4, I know a few things that you guys don't know, so I know that's approximately 0.7. At pi over 2, that would be 0. At 3 pi over 2, that'd be negative 0.7. We're looking at this tangent line at 3 pi over 4. At pi, that would be negative 1. At 5 pi over 4, that would be negative 0.7. At pi over 2 would be 0. At 7 pi over 4, that'd be positive 0.7. And at 2 pi, that would be positive 1. If we were to plot those points on our graph, we get the point 0, 1, the point pi over 4, 0.7. It's about right there. Pi over 2 is at 0. 3 pi over 4 would be at negative 0.7. Pi would be all the way down at negative 1. 5 pi over 4 would be at negative 0.7. 3 pi over 2 would be back at 0. 7 pi over 4 would be up at 0.7. And 2 pi would be all the way back up at 1. And we were to connect those dots. If we remember what we learned in pre-calculus about the graphs of sine and cosine does start at the top. So the derivative of f of x equals sine x, it looks like that would be cosine x in this case. All right, let's try the same thing with the graph of cosine x. We're going to sketch these tangent lines. There's one there at 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. If you need to, you can pause these videos and take a little bit of time to see what those tangent lines are. All right, so if we were to pick those values, the slope at 0 is 0. Slope at 0 is 0. The slope at pi over 4 would be this negative 0.7. Pi over 2 would be negative 1. 3 pi over 4 would be negative 0.7. Pi would be 0. 5 pi over 4 would be 0.7. 3 pi over 2 would be 1. 7 pi over 4 would be 0.7. And 2 pi would be 0. So let's plot those and see what the derivative graph is similar to. So first point says 0, 0. We got negative 0.7, negative 1. 3 pi over 4 is back to negative 0.7. Pi is back to 0. 5 pi over 4, positive 0.7. 3 pi over 2 is at 1. And 7 pi over 4 is at 0.7. So we're going back down again. And 2 pi is back as 0. If we were to connect those dots, we see that this is also looks like a trig function. Since it starts at the origin, I would consider that sine. But since we are going down first in the negative direction from 0 to pi over 4, this would suggest that the derivative is negative sine x, derivative of cosine. And that is, in fact, true. So we can add these to our toolbox. The derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. So these derivatives and some identities can be used to prove these other derivatives. So tangent x is equal to sine x over cosine x. And we're going to use the quotient rule for that. The quotient rule, low d high minus high d low all over low squared. So y prime would be equal to cosine x times the derivative of sine x is cosine x minus the top sine x times the derivative of cosine x, which is negative sine x, all over the denominator, which is cosine squared x. And now we do some simplifying. Cosine times cosine is cosine squared. Negative sine times negative sine is positive sine squared, all over cosine squared. Sine squared plus cosine squared, the numerator here, we're going to use this identity up here. Sine squared plus cosine squared is equal to 1. So we get 1 over cosine squared x, and 1 over cosine squared x is secant squared x. So the derivative of tangent is secant squared. So we can do the same. Cosecant is 1 over sine. We're going to use quotient rule for this. So the denominator times the derivative of the top would be 0 minus 1 times the derivative of sine x is cosine x, all over sine squared x. That's just using the quotient rule there. Sine x times 0 is just 0. Negative 1 times cosine x is negative cosine x, all over sine squared x. We can break that sine squared x into 2 different pieces. Sine squared is just sine times sine. So we're going to do negative cosine over sine times 1 over sine. Negative cosine over sine is negative cotangent x, if you remember your identities from pre-cal. And 1 over sine is cosecant x. To make this match our notes, we're just going to switch, put the cosecant x in front, and cotangent x. So the derivative of cosecant x is negative cosecant x cotangent x. Secant x is 1 over cosine x. And we're going to do this similar as to what we just did. Y prime would be cosine x, the denominator, times the derivative of the numerator is 0, minus 1 times the derivative of cosine is negative sine x, all over cosine squared x. We take this and we cross out the cosine x times 0 because that goes to 0. Negative 1 times negative sine x is positive sine x. And we can go ahead and break the cosine squared up like we did in the previous proof. Sine x over cosine x is tangent x, and 1 over cosine x is secant x. And to make this match our notes that we're going to see in just a second, that is secant x times tangent x. Alrighty, we're looking at y equals cotangent x now. This would be equal to all right, y equals cotangent x. This would be equal to cosine x over sine x. We're going to use quotient rule again for that. Low d high minus high d low, all over low squared. mighty low, all over low squared. So y prime be equal to the denominator, sine x, times the derivative of cosine x is negative sine x, minus cosine x times the derivative of sine x is also cosine x, all over the denominator, which is sine squared x. Sine times negative sine is negative sine squared. Negative cosine times cosine is negative cosine. We can factor a -1 out of this numerator, so we can use our Pythagorean identity. So -1 times sine squared x plus cosine squared x all over sine squared x. Sine squared x plus cosine squared x is just 1, so the numerator is -1. Denominator sine squared, and -1 over sine squared is negative cosecant squared. All righty, we have proved these four. So the trig functions, we now have a nice box here to help us. Now, we must know these, especially this sine and cosine. Trig functions, trig derivatives tend to come from the first column, but all must be memorized. Note that trig functions beginning with C have derivatives that are negative. So cosine is negative, cosecant is negative, cotangent is negative. That's just one of those things that we can remember to help us figure this out. Now, if we were to look at this idea of cosecant and secant, there's a nice way that we can remember that derivative of tangent, and we have secant and secant. So if we look at this, the derivative of tangent, ddx of tangent x, would be, if we go from left to right, the derivative of tangent would be secant times secant, which is secant squared x. And if we were to go from the left, the derivative of secant x would be equal to secant x tangent x. So maybe this is just something that can help us remember that. The same is true for cotangent. I'm going to put a negative cosecant in the middle. Now, if we look at this, the derivative of cotangent, if we read this from left to right, derivative of cotangent would be negative cosecant times cosecant, which is negative cosecant squared. And if we were to read this from right to left, derivative of cosecant would be negative cosecant cotangent. So maybe that's something that can help us remember the derivatives of tangent, cotangent, secant, and cosecant. All righty. The derivatives of sine and cosine are cyclic. We can see this by taking higher order derivatives. If we just continue to take derivatives over and over and over again, we will see the cyclic pattern. The derivative of sine x is cosine x. Derivative of cosine x is negative sine x. Derivative of sine x is cosine x, but since it's negative, that's going to be negative cosine x. And the derivative of cosine x is negative sine x, but we already have a negative, so two negatives are going to end up being a positive sine x. And we see we're back to where we started. So derivative of sine x, cosine x, derivative of cosine x is negative sine x. And the derivative of negative sine x would be negative cosine x, because derivative of sine is cosine, and the sine is negative. Derivative of cosine is negative sine, but we would have two negatives, which end up giving us a positive sine x. Derivatives of cosine are also cyclic in nature. Derivative of cosine is negative sine. Derivative of negative sine would be negative cosine. Derivative of negative cosine would be positive sine, and derivative of sine gives us back to cosine. The next four would be similar. There's a nice way that we can remember these derivatives of sine and cosine, whether they be positive or negative. Since they are cyclic, it's this idea of a clock. Sine x, cosine x, negative sine x, and negative cosine x. So if we were to go clockwise, the derivative of sine x is cosine x. the derivative of cosine x is negative sine x. The derivative of negative sine x is negative cosine x. And the derivative of negative cosine x is positive sine x. This is going to be really useful when we start taking antiderivatives in a later chapter. And the antiderivatives are just going to be read in the opposite direction, counterclockwise. So this is something that can just help us keep this in order here. So if we were looking for the 50th derivative of sine, we would start at sine, and you could literally count 1, 2, 3, 4, 5. We could go through and count all the way to 50. Or we could divide 50 by 4 and just see where we are in this pattern. 50 divided by 4. 50 goes into 4 goes into 5 one time. We multiply, we subtract. 4 goes into 10 two times. We multiply, we get 8. We subtract, our remainder is 2. So if we start at sine x, our remainder would be 2. So that's going to put us down here at negative sine x. And for the 50th derivative of cosine, we still get a remainder of 2, but we're starting at positive cosine this time. So 2 after positive cosine. We now have 4 basic derivative forms. We got the power rule, the product rule, the quotient rule, and trig. And chain rule is always in effect. Just because there's a power in the problem doesn't mean it's power rule. Just because there's a trig function doesn't mean it's a trig form. It could be one of the other forms. So let's start taking some derivatives that involve trig functions. This x, there's nothing inside there. So that's nice. We don't have any powers. We don't have a product. So this is just basic trig form. And y prime would be equal to 2 times the derivative of sine x, which is cosine x, times the derivative of x, which is just 1. So that chain rule still comes into play there. This sign has a 2x. We can put that in parentheses so that we can see this as the inside function. And we're definitely going to have to use chain rule in this case. Derivative of sine is cosine. We're going to leave the inside function alone, and then we're going to multiply that by the derivative of the inside function, which is 2x. And derivative of 2x is just 2. So we get 2 cosine 2x. And we don't have to write the derivative. I'm sorry, not the derivative, the parentheses there if we don't want to. Y prime, we still get this 2x. It's still the inside function. So 2 times the derivative of sine is cosine. Chain rule says to leave the inside function alone and then multiply by the derivative of the 2x, which would be 2. We can clean that up a little bit. 2 times 2 is 4 cosine 2x. Part D, y equals sine squared x. Typically, notation, we put the squared in between the sine and the angle. That way we don't get confused. So this means the entire expression is being squared as opposed to just the x being squared. Those are 2 different expressions. And when the squared is between the sine and the angle, the entire expression is being squared, not just the variable x. So this would be power rule. We have something raised to a power. So to take that derivative, we're going to use the power rule. The 2 comes down in front. We multiply the 2 in front. We subtract 1 from that exponent. 2 minus 1 is 1. And then we multiply that by the derivative of what's inside the parentheses there. So we get 2 sine x. And the derivative of sine x is cosine x. Looking at part E, we do have the entire expression being squared again. So we have sine 2x. And that entire thing is being squared. So again, this would be power rule. So to take the derivative, we have something raised to the second power. So the derivative of that is going to be 2 times something raised to the first power. And we're not changing the something inside. And then we're going to multiply that by the derivative of sine 2x. And the derivative of sine 2x would be cosine 2x. But since this 2x is still an inside function, we're going to have to use chain rule one more time. And the derivative of 2x is 2. We can multiply the 2's together. 2 times 2 is 4. So we get 4 sine 2x times cosine 2x. Part F, we got sine of the square root of x, which if we put this in notation that we familiar with. That would be sine x to the 1/2. Notice only the x is being raised to the 1/2 power here, not the entire expression. So this would be a trig form, and the derivative of sine is cosine. So we get cosine x to the 1/2. We're not changing that part. And then we're going to multiply that by the derivative of x to the 1/2. Derivative of x to the 1/2 would be 1/2 x to the, we're going to subtract 1 from the exponent. That would be -1 half. And then we can clear that up a little. Switching to identicals, so choose, we can x, or cosine of the squared x, the 2 in the denominator, we can move the x to the -1/2 to the denominator, making it +1/2, which would also be square root of x. So we've taken the derivative of that function. I think I'm going to stop here. That's probably long enough for this video. And then we will look at part 2. We'll finish the next 2 pages. Shouldn't take us long in the next video, maybe 20 minutes or so. If you have any questions, please send me a message on Remind or through email, and I'll get back to you as soon as I possibly can.